Hello! In this lesson, we will learn about relative motion. To explain what this means, let's start with an example. Imagine two kids are playing catch with a football. Jane is standing still, holding the football, and Joe is running away from her, waiting for the pass. Jane then throws the ball low and fast. How long will it take for the ball to reach Joe? There are two ways we can solve this problem. Let's start with the way we are hopefully more familiar with. When Jane throws the ball, Joe has already run some distance d away. Since Jane is standing still, we will treat her as the origin of our line. She throws the ball at some velocity, which we will label VBO, which means the velocity of the ball as measured by someone standing at the origin, which is Jane. Meanwhile, Joe is running at some velocity, which we label as VJO, which is the velocity of Joe as measured by Jane at the origin. Now, what we are looking for is the moment in time where the position of the ball equals the position of Joe. So on the one hand, we know that the position of the ball is given by VBO times t. On the other hand, the position of Joe is given by VJO times t plus d, since at the moment the ball was thrown, Joe was already some distance away from Jane. So now we set these two equal to each other, and we solve for time. I recommend pausing here and trying to do it yourself before watching me do it. The first step in solving for time is to move all terms that have t in them over to the same side. So we will subtract VJO times t by both sides. Now that those two t terms are together, we will factor out their common t. Then we divide both sides by VBO minus VJO, and are left with this equation. So now we have solved for time, which is what we wanted to do. But you can think of this problem a bit differently. Imagine that we consider the problem from Joe's perspective, not Jane's. From his perspective, he is running away from the ball, but it is coming towards him. So the speed between the ball and himself is actually the difference between his speed running away from it and its speed coming towards him. So we can write that like this, where VBJ is the speed of the ball as Joe sees it. If you aren't quite sure why I chose this order of subtraction, think about it like this. Imagine the ball is moving faster than Joe, which it has to be if it will ever make it to him. Then, written in this order, we will have a positive quantity, which means that, from Joe's perspective, the ball is moving to the right, which is what makes sense. So this is the correct order of subtraction. Now, the distance that the ball has to cover relative to Joe is d. Therefore, the time required for the ball to reach Joe is d divided by VBJ, which is the same answer we got from before. So now we have solved the same problem by considering relative velocities. Very often, this way of thinking will be a lot more helpful. We can arrange this equation to get the following equation. VBJ plus VJO equals VBO. This equation is very useful when working with relative motion, but we have to define how to read it and how to work with it. So again, the first letter is the object that is moving, and the second letter is the object or place that is observing. Now, we find the shared letter between the two velocities, which in this case is j. Now, when we add these two velocities together, we end up with a result whose shared letter disappears and whose other two letters remain where they were. While this might seem a bit confusing, it really is very powerful, because you can construct this kind of equation for any situation where there is relative motion. Once you construct the equation, you will be able to manipulate that equation to solve for the velocity that you want. Now, one more point before we see an example. We can flip the letters, which means that we are flipping who the observer is and who the mover is. If we do that though, we have to also make it negative. Therefore, we can write this equation. To explain how this makes sense, from Joe's perspective, the ball is moving towards him, which is rightward. But from the ball's perspective, Joe is moving towards the ball, which is leftward. That is why you have to change the sign. Now, let's take what we have learned and solve another example. Imagine you have two bumper cars that are approaching each other head-on. Bumper car A is moving at 2 meters per second, and from his perspective, bumper car B is approaching at 5 meters per second. How fast is the car B moving as observed by someone standing on the ground? I suggest pausing here and trying to solve the problem yourself, either by using the formula from before or just your own sense of logic. So, what we want to solve for is VBO, which means the velocity of bumper car B as observed by someone standing at the origin, which is the unmoving ground. The information we are given is the velocity of car A as observed by the origin, and we are given the velocity of bumper car B as observed by A. With that information, we will write an equation where we add two velocities that share a letter. In this case, that will be A, which is shared by our two givens. So we add our givens together. Now, we know that this equals a quantity where we remove the common letter and keep the other two letters where they belong. Hey, would you look at that? The result is the velocity of B with respect to the ground. which is exactly what we wanted. Let's plug in the values now. Note that VBA is negative 5 because it is moving leftward. We find that car B is moving 3 meters per second leftward as measured by someone on the ground. I hope this was helpful. Good luck.